Good morning or good afternoon, everyone. Welcome to our next installment of VisualSim training series. Today we're going to learn about how to build performance models of proposed system architecture to make architectural decisions to meet your design requirements. For example, the performance or power and things like that. But in this installment, we will not be doing power analysis, but in the coming tutorials, we'll be taking that as well. Those of you who are having VisualSim installed on your machine, I would recommend you to keep it ready. And if you do not have, you can try to use our online version of the tool using the link given below, and make sure that you're opening up this link using Internet Explorer or Firefox. Okay. So before we get started with today's web training series, I'd like to go over a few logistics details. Um, You can see a chat window or a control panel on your desktop right-hand side. You can post in your questions in the chat window, and we have people in standby. They'll be answering your questions. And also, I'll be taking up these questions at the end as well. So here's a quick outline to today's training series. Here today, I'll be starting off with a brief overview for what we did in the previous session. And I'm going to talk about what is performance modeling and what are the type of analysis that you can conduct and what are the kind of design decisions that you can come up with if you do a performance modeling. And also I'll be talking about how can you select the library blocks to represent a piece of hardware architecture or piece of software of your proposed system architecture itself. And I'm going to go over a few experiments and hands-on modeling exercises as well. At this point, I would like to recommend you to follow me the way how I go across the modeling. And also, we will send you the tutorial links after this webinar. You can actually practice in offline. So in our previous training session, we actually started off with a very basic introduction to VisualSim, and we learned about the modeling concepts. For example, what is a data structure and what is the requirement, or why do we need a data structure? And then we learned about few very basic regex expressions as well. And also we learned about selection of library blocks to update the data structure itself, or to define a queue, or to generate some statistics and all that. And also we learned about how to use a parameter, which actually allows a designer to make modifications or changes to the system architecture uh, during every simulation run, and try to understand what is the kind of reports or what is the kind of trade-off that the designer is getting out of the system constructed. Okay, so with regards to performance level modeling, performance modeling is a structured and repeatable approach to perform architectural decisions. When we say architectural decisions, it could be selection of a processor itself, or it could be selection of the memory subsystem, or it could be the selection of the right bus interface, and how do you distribute your tasks between your multi-core and multi-processor platforms. And also if you have multiple processing resources, for example, a processor and a FPGA and an ASIC, so how do you distribute your applications between these different processing resources to get maximum performance, or to meet your performance goals. And also it could be a selection of the scheduling algorithms itself, what kind of scheduling algorithms that you need for your real-time operating system. And also it could be flow control and buffer management as well. So what kind of flow control algorithm that you need to have a lossless and still able to meet your performance requirements and things like that as well. And this is the list of kind of very important list, I would say, and not an exhaustive list, and it can actually go up to all functional and non-functional characteristics of a system itself. And the main idea of conducting performance modeling is to make sure that you are doing a kind of quantitative assessment based on the characteristics that you get, or the kind of performance characteristics that you look at. For example, it could be the performance latency, processing latency, or it could be the end-to-end latency, or it could be the dependencies between multiple tasks and impact of that dependency on the latency of your task processing itself. Or it could be a throughput of a particular bus or MIPS for your processor, or it could be IOPS for your memory system, things like that. And also it could be utilization of the resources as well. So how much your processor is being utilized, whether it is being underutilized or whether it is being overutilized, and things like that. And these are the kind of quantitative assessment will actually make sure that the architectural elements that you're selecting are not based on any guesswork, but instead you have conducted a lot of analysis on the architecture that you're selecting and make sure that the architecture is going to work after implementation without any problems. With regards to VisualSim for performance analysis, we capture all the characteristics that I just talked about, and also it goes beyond the characteristics that I talked about and covers functional and non-functional performance characteristics of an embedded system or system, it's an electronic system as well. For conducting performance analysis, a VisualSim model should contain at least 3 of these below contents. For example, you need to have the resources that are used. For example, it could be your processors, memories, or it could be the scheduler for your real-time operating system, or it could be the semaphore itself, or it could be the kind of use cases that you're gonna implement in your real system as well, kind of some representative scenarios. So how exactly the system is going to behave for a set of use cases as well. And also you need to consider, you need to have the workload intensity for each of these different scenarios that you are going to implement as well. So what would be the arrival rate for the requests? And also, is there any kind of dependencies between multiple use cases or multiple tasks or things like that as well? And also whether there are any kind of concurrent task processing that is required to happen in the platform as well. So as a whole, a VisualSim model must contain the architectural elements of your system platform, including your processors and buses and memories and things like that. And also it must include the use cases or behavior flow for your applications that you're going to run on the real platform. And also you need to consider the rate at which different devices are running, or rate at which the workload is operating, and things like that as well. So with a performance model in VisualSim, you can achieve a lot of things. For example, you will be knowing exactly why a particular processor has been selected and what is the reason behind it. And also it allows you to understand where exactly you need to store your program. For example, you need to have it in your local memory, or it must be stored in a remote memory and things like that. And what would be the reason for a contention of a particular resource? How can I avoid those contentions and things like that? And also you can have the system which includes relationship between multiple components and multiple resources as well. So what would be the impact of those dependencies on the total system performance? And, and in addition to that, if you have multiple processing resources, how do I distribute my programs or my tasks between multiple processing resources? So which would be my optimal mapping methodology that I can go with to achieve the performance and power requirements that I'm looking for? So apart from these, what you can do is you can actually share these simulation models with designers and customers to validate the system architecture that you have constructed to gather more information, or it could be handed off as a golden reference file for the implementation team to follow as well. So now I'm actually moving over to an example, kind of tutorial. I'm going to build the model step by step that actually you can actually follow the way how I'm constructing the model as well. So the example that I'm going to consider for today is embedded board design. So here what I'm going to do is the major focus of this particular tutorial is to size the system configuration for processor speed, memory utilization, and latency. So we are going to look at what would be the utilization of my processor if I'm actually running at a particular clock speed with a certain set of workloads. And also I'm going to look at what is going to be my memory requirements as well for the set of tasks that I'm running on the platform. If I'm running a different set of workloads, what would be the kind of impact on my total system performance as well. I'm also going to look at possible system bottlenecks as well. So what would be the kind of threshold limit for successful processing of all the tasks, and what would be the upper bound without having any kind of memory overflow and things like that. And also I'm going to look at how can I compute latency for each tasks as well. So when I say here latency, we can either consider in terms of processing latency, or it could be end-to-end latency as well. So end-to-end latency will be very crucial because that will actually allow you to capture the kind of dependencies that would cause the performance-related issues as well. So you will know which part of the system is actually causing the performance-related issues. Okay, and also I'm going to look at how can I define my software behavior flow as well with task dependencies. So you may actually wait for completion of a particular task, and if that particular task takes more time than expected, then you would end up taking more time for the task that is actually dependent on the previous task as well. So we're going to look at all these scenarios as well today. So here's a kind of very high-level block diagram of the proposed system architecture. So in this case, I'm going to have 3 different tasks, and task 1 is a kind of sequentially, it generates transactions or requests at certain rate, and task 2 is actually dependent on task 2 is dependent on task 1. Every 5th transaction is actually going to trigger the task 2 request. And again, I have one more task called task 3 that is going to be a kind of uniform distribution of the requests that are going to go into the processor platform. So in this case, what we have here is a simple processor and a memory resource. So what we have done here is we have defined some descriptions for all the tasks that I'm going to run. In this case, I have 3 tasks. Task 1 will be having highest priority, and it will actually have a inter-arrival time of 2 milliseconds. And the execution time is going to be about 10 microseconds. So when I say execution time, this is purely related to how many number of instructions that you have for that particular task and how long that particular task is going to run on the target platform. This can be computed based on the instruction trace files, or it could be computed based on if you have any trace files generated from the real systems as well. And task 1 requires about 20 bytes of memory space as well, whereas task 2 requires medium priority, and for every 5th task of task 1, it is going to generate a task 2, and the execution length is going to be about 4 milliseconds, and the memory it is going to take is about 100 bytes. And then we have task 3, which is of lowest priority, And the intra-arrival time is going to be kind of uniform distribution between 80 to 120 milliseconds. And task 3 itself will actually spawn 3 different tasks, or I would say 2 different tasks actually. So again, those will be having different set of priorities and or same set of priority but different set of execution length and memory requirements as well. So here's a kind of detailed block diagram of the proposed system. So here we have 3 different tasks, and then you have a memory access before doing any processing on the CPU. And then you have your CPU processing itself, which will be taking your execution length, what you already have in the task definitions. And once your processing is over, you will be releasing that particular memory. For example, in this scenario, we're going to consider about 1 kilobyte of memory for all the tasks, and we're going to utilize the memory of given or of whatever the definitions that we have here, 100 bytes or 200 bytes, that will be actually taken from 1 kilobyte of memory itself. And then if we have task 1 or task 2, then you will complete the task and you generate the latency for it, and you'll be knowing what is the total end-to-end delay between your at what time you have generated the task and what time it has completed. If it is function 3 or task 3, it is going to generate function 4 and function 5. So that actually again goes back to access memory, CPU processing, and release memory. So this is what we are going to do today. And if you come across any questions while I'm constructing the model, you can post in your questions in the chat window. I can stop and I can go back and explain that in detail. So what I'm going to do at this point is I'm going to head over to VisualSim Architect. I'm going to open up I already have a new block diagram window. And here what I'm going to do for first is I need to instantiate the digital simulator itself. So this is the very first thing that you would be doing. And after that, what you have is you're going to define the stop time, but now I'm going to wait for some other parameters to enter. For example, what I can do is I can actually parameterize stop time for my digital simulator. I can say how long I need to run my model. So in this case, I'm going to say that I'm going to run this model for about 50 microseconds. And then I'm going to define certain parameters. For example, as you know that I mentioned that we're going to have about 1 kilobyte of memory space for the embedded board that we are looking at. And what I'm going to call here is memory capacity. And I'm going to provide a 1 kilobyte of memory space. And then what I'm going to do is I'm going to have a can I keep it as it is? So what I'm going to do is, as you have noticed in the block diagram, I need to have a CPU for doing processing activities. So to represent a CPU, I'm going to bring in a system resource block. A system resource block includes the processing resource as well as the scheduler, which actually represents a part of the real-time operating system as well. I'm going to call this as processor, and I'm going to run this processor at 1 megahertz. And then I'm going to set this time type to number of clocks, which means I'm going to consider the clock rate megahertz over here, and I'm going to consider how many cycles each of these tasks are going to run. And again, I'm going to select the scheduler type to first come first serve plus preemption over here. So this defines my processing resource over here. And again, this is not a detailed processor model that we're constructing here because we are doing a performance level modeling and we don't really need instruction level processing at this particular point. Okay, so this defines my processor for my system architecture. So now what I need is I need to generate 3 tasks as I shown in the system model. I'm going to instantiate a traffic block which actually helps me in generating traffic triggers for the for different type of tasks that I have. I'm going to set the time over here. For example, I'm going to set this to 1 microseconds. And then what I'm going to do is I'm going to define some task definitions. For example, if you notice in the slide, what I had mentioned was task 1 is going to have highest priority. I'm going to define those priority details over here. I'm going to say task number is going to be first. This is my first task. And then I'm going to mention the task priority as 3. As we have 3 tasks, I'm going to set this to highest priority. And then what I'm going to do is I'm going to mention what is the memory that I need, memory required. And this is about 20 bytes that I'm actually requesting, or this particular task is requesting. And again, what I have in addition to that, what I have here is I have the execution time details as well. So this task is going to run for about 10 microseconds. I'm going to consider some smaller value so that I can run it for a shorter time period. This can be varied as well. I'm going to commit this. So these 2 blocks actually generates my task definitions for my task 1. So I can call this as my task 1. So now what I need to do is for every 5th task, I need to generate a task 2. To do that, what I'm going to need is I'm going to need a block called fork. So what it does is it'll actually just splits the incoming transaction into 2 parts. So what I can do is one task can actually immediately go to CPU for processing, while the other one will actually consider the scenario like I need to have or I need to generate task 2 for every 5th task. So what I'm going to do at this point is I'm going to consider a memory variable. I'm going to define it later. I just call it as F2 counter. And what I'm going to do is I'm going to simply add up this and then going to create a condition to check if my F2 counter has reached number 5, or did I generate 5 F1 task. So I'm gonna just set this to true or false. If I generate 5, yes, I have generated. If not, I'm gonna set this to false. And then what I'm going to do is I'm gonna again use this in case if we have reached 5, I need to reset this F2 counter so that I can start it again. If this is going to be true, then I'm going to set this to 0, and if not, it is going to be the same value which was defined previously. So now we have defined a condition here, or a kind of logic here, to make sure that for every 5 tasks, 5 task 1s, I'm going to generate a task 2. So now I need to define the definitions for my task 2 here. So I'm going to need task number, which is going to be task 2 or 2, and priority is going to be 2 because this has lesser priority than the first one. And then I have execution length, and this is going to be about Let us consider some number, maybe 20 e power minus 7. And then what I'm going to do is I'm gonna need to know what is the memory that I need. I'm gonna set this to memory requested is about 100 bytes. So this defines my task definitions for my task 2 as well. So task 2 must be generated only if the F2 counter reaches 5, or if you have generated 5 F1 tasks. So this condition will actually make sure that you're gonna send only once or only when your counter reaches the value 5. Okay, so I'm gonna commit at this point. So now you have task 1 and task 2. Now I can define my task 3 as well. I'm gonna just copy and paste it, and I'm gonna leave it as it is for now. Later we can actually change it for based on the requirements that we need. And task number, I'm gonna make it as 3, and priority, I'm gonna make it as 1. And the memory request that I need is about 500 bytes, for example, let us say. Whereas we have a total of 1,000 kilobytes, or 1 kilobyte, sorry. So I'm gonna consider it as 300 bytes here. So this is going to take about 1.3 e power minus 7. So now I have defined my task 1, task 2, and task 3. But now we need to map this, all the task definitions, what we did here, to run on the target processor platform here. And also, if you look at the block diagram that we had earlier, we need to consider memory access as well. And after that, we need to do the CPU processing, and then we need to release the memory. So I'm going to do the same thing. So what I need at this point is I'm going to need join blocks that actually allows me to connect all these transactions in, going to the same uh, direction. So we can't really add additional ports to these join blocks. That's why we need to have two join blocks here. So what I'm going to do at this point is I have joined all these blocks. Now what we need is we need a memory request. So to model the memory, what I'm going to do is I'm going to bring in a block called quantity shade or resource allocate memory here. So this actually helps me in defining the memory or the memory bank, and what is the total size of the memory that you're considering as well. I'm going to double click on this, and I'm going to define the parameters here. So the resource capacity is the mem capacity that we have defined as a parameter at the top. It is 1000 bytes. And the maximum queue occupancy, so this is something like the requests or memory requests that are still waiting for servicing or processing. So this can be any values based on your requirements. In this case, I'm going to stick with 30 over here. And this number of dimension in this scenario could be, this is going to be your memory bank, how many banks you have. In this case, I'm going to consider as a single bank, and a single bank of memory I'm having about 1000 bytes. If you have multiple memory banks, you can actually split this to multiple, and you need to share your memory capacity across all the banks itself. Okay, so I'm going to commit this, and once you have your memory allocation, you need to free that allocated memory. To do that, you can use the block called resource QS free that goes with resource QS allocate priority block. I can rename this block as DRAM because it represents my memory, and I can rename this particular block as memory free. Okay, so now we have the DRAM and we have a way to release the memory as well. And to be able to connect the behavior flow or the tasks onto the processing platform, we can use a block called mapper. So you just need to define the name of the processor or the scheduler where you are running, and you need to define the task number, which task you're running on your processor, and what is the priority associated with that. Priority associated with that, and you're going to define what is the execution length or how long you're running that particular task itself. So these are the kind of definitions that you do over here. So what happens over here is, as we are providing priority over here and the processor supports preemption, so highest priority tasks will be actually processed first, and if there are no more highest priority tasks, then the least priority tasks will be taken for processing itself. So now we have the complete picture of the behavior flow here. We have the memory request, we have the processing of the processing on the CPU, and also we have a mechanism to free the memory that we have allocated for different of tasks that we are running on the platform here. And if you look at over here, the block or the resource allocation block requires a few ports. For example, it requires the complete data structure values that are coming in. And also this requires quantity request as well, which translates into if task 1 arrives over here, task 1 will actually tell the memory allocation resource saying that I need 20 bytes of memory space out of 1 kilobyte. So that particular request will be actually sent through this particular port, whereas the priority port requires the priority of that particular transaction. And then you have this dimension that tells you in which memory bank that you are trying to access. If you notice here, the data structure will actually have combination of all these details, just that we need to split up all these details into different ports, and we need to send it to the right ports itself. So what I'm going to do at this point is I'm going to bring in an expression list block, which actually helps me to split up all these different uh, data structure fields to the corresponding blocks. I'm going to double click and I'm going to delete all the expression list details here. And I'm going to name different ports here. For example, I need a port to do memory request, and then I'm going to need a port for priority, and I'm going to need a port that actually helps me to get the memory bank. And then the kind of values that you're going to send it across would be, for memory request, you'll be sending the memory request. This is the field that you have actually added in the expression list right after the processing block over here. And then you have your priority that you need to send it across. And then for the memory bank, as we are considering only one memory bank, I'm going to set this directly to 1. And then I'm going to set these to true, which means all the time you can actually send it across. There is no output conditions that is controlling these mappings. Okay, so I'm going to set all these values and I'm going to commit. Now I need to generate or create ports for the ones that I just created, and I'm going to do that right now. The ports are memory request, and it is an output port, and it is going to send the integer value. And then I'm going to need a port called priority, and it is again a output port, and it sends it across integer value. And then I have the memory bank output port, and it is going to send an integer value. I'm going to make this to south to make it nice and clean. I'm going to commit this. I'm going to connect all these ports to the corresponding ones. Okay, so now we have the complete setup over here. So we are defining the different tasks, task 1, task 2, and task 3 at different rates, and you have the dependencies defined as well. And then you are actually requesting for the memory for whichever the tasks that you're running, and then you will be running on the processor over here. So as soon as task enters into this mapper block, it will actually send control over to the processor over here, and based on the rate at which you're running and what is the execution time that you have provided, it is going to run for that particular time period. And then once the processing is over, it will free the memory. So this completes the task definitions over here. At this point, we can actually go ahead and generate some statistics or end-to-end latencies and all those stuff. What I'm going to do is I'm going to capture end-to-end latency over here. So T now returns the current timestamp minus input.time returns at what time that particular transaction was generated. I'm going to change this output type to double so that I can capture my capture the end-to-end latency. I'm going to bring in a time data plotter, so that actually helps me to capture my latency versus simulation time. And then what I can do is in order to understand the memory utilization details, we can actually capture the memory requirements right from this particular block itself. So all you need to do is you need to connect a text display to stats block of this DRAM block. And then what you need is you need to send a integer value at what time that you need to generate. I'm going to call this as, I'm going to generate a trigger at the end of the simulation time. I'm going to make this as integer, so just in case. So what it does is it is going to generate the memory statistics at the end of the simulation. So what else we can do is, in order to understand how much processor is being utilized, I'm going to generate the statistics for the processor as well. So in order to do that, I'm going to bring in a block called resource statistics. I'm going to define the name of the scheduler or the block that I'm using. It is processor, and I'm going to generate one sample. I'm going to keep this as blank. I'm going to set this to sim time over here. I'm going to connect a text display over here. So I'm going to set this stop time to sim time here and run the model. So it is going to, for example, if you see over here, the model is actually incomplete. For example, I have actually used a memory called F2 counter, or a variable called F2 counter, but it is not initialized anywhere in the model. To do that, what I need is, if you notice here, it will actually highlight that particular block itself, and also it will give you an information on what exactly the problem is. So I'm going to instantiate a variable list. I'm going to call this variable as F2 counter. I'm going to initialize this with value 0. So I'm going to again run the model, try to understand what is going to be the problem. So if you see here, it looks like I have a either a spelling mistake or the kind of value that you're sending is not correct. Okay, so it is actually, that is the case. So what I'm going to do now is, if you see here, some places have actually named it as execution length, whereas in some places I have named it as execution time. So those kind of differences must not be there, and it must be the exactly same. And also VisualSim is more of uh, case sensitive, which means if you use a uppercase letter, you must use the same thing if you are reusing that particular field somewhere else in the model. Otherwise, it will be considered as a completely new or a completely different field. So if you see over here, we are actually generating some statistics here. So this tells you that the processor is hardly utilized, it is very less. And also the memory that we have used is about a maximum of 420 bytes of memory, right? And also this tells you that you can run much more tasks on the same platform. Now what we can do is we can actually increase the load on the target platform, and we can start sending the transactions at a higher rate. For example, let us send it at every 100 nanoseconds, and what is going to be the impact of that on the resource utilizations, right? So the memory requirements did not really change much, whereas utilization of the resources changed a little bit. Okay, so in the real system, or in the definitions what we had earlier, the requirement was actually to send this particular task 1 at 0.002, and the other one, like task 3, must be generated at 0.08 with a uniform distribution between value 1 and value 2 over here. I'm going to set as it is. And then what we had was we had additional details, such as we had task 3 generating task 4 and 5. To do that, we actually we can use a script block to define the definitions of all the internal details. To do that, what I'm going to do is I'm going to bring in a script block, and I'm going to load the script to generate the details. I'm not going to write it, as it takes a little while. I'm going to paste the details over here. But if you look at this particular script over here, this is exactly like a C language. And if you see here, the first portion is actually we are computing the end-to-end latency, while the second portion we are actually looking at which task we have received. And based on that particular task, we are going to generate the tasks. For example, if the task number is 3, we're going to generate a task number 4 with a memory request of about 100 bytes. I'm going to change this for my model. Memory request, and this is going to be the task number. I'm going to change this execution length to about some other number. Okay, I'm going to change this as well. Okay, so in this case we are capturing or we are generating the tasks based on the previous tasks here as well. So there is a dependency over here. So the additional script requires, or the script requires additional ports here. So I need to generate, or I need to define those. For example, we are generating the latency for each flows or each tasks. And in this case, plot is going to generate the latency for my task 1. Plot 1 is going to generate latency plot for my for task 2, whereas plot 3 or plot 2 is going to generate latency for task 5, which is actually generated by task 3, right? And then if you receive task 3 and task 4, it is going to spawn the additional processes like task 4 and task 5. So I'm going to generate that as well. I'm going to keep that to south to make it more nice and clean. I'm going to connect this feedback loop all the way back to this join block. So this actually helps me to, if there is any kind of task 3 and task 4s that are coming back here, or task 4 and task 5 will be actually generated by this script block over here. And all the 3 blocks or 3 ports are corresponding to the latency itself. Okay, so now we have much more complex scenario here. So initially you actually had a dependency over here, but later on we actually added a dependency to generate 2 additional tasks after completion of task 1 or task 3 itself. Okay, so in this case, if you notice, task 3 is actually having a priority of 1 here, and also it should be the same in this scenario as well. It can be different. It's not a problem. So I'm going to generate, or I'm going to run the model. Okay, I'm going to this for a short time period. So if you see here, it's hardly utilized. So I'm going to just increase the rate. I'm going to run the model again. So it still tells me that I'm actually not running my system at a full potential. So what I can do is I can actually still increase the rate at which I'm actually generating the transactions. For example, for every 1 nanoseconds, I can generate the traffic. And here I can actually reducing the execution length, or that's the option. Okay, so I'm going to run the model, try to see what is going to be the impact of increased rate. So in this case, we are actually seeing there are a lot of transactions that are going across, but the time that processor takes to process all the transactions are very less. That actually tells you that the load on the processor is not very much, and you're completing all the tasks at a very lesser time period. If you see here, the total delay time is very less. This actually tells me that I can actually increase the execution length. For example, I'm going to make this to about 2.0, and I'm going to see what is going to be the impact of it. If you see here, now what I did was I actually increased the processing time of the processor at a greater level. And if you see here, the number of transactions entered is hardly about 48, and exited are about 24, and remaining 24 tasks are still waiting for processing. And if you look at the utilization here, it is about 96% your processor is being utilized. And if you look at the memory here, it is actually completely utilized here. So you definitely need that much. But this actually tells you that you may actually need additional 500 bytes of data to be in the safer side. So these kind of analysis will actually help you to make decisions on how much memory that I need to have, and what should be the processor that I need to be using, and also what should be the clock rate at which I'm going to run that particular process itself. So by this tutorial, we actually learned that how exactly the workload or the kind of traffic rates is going to impact on your memory requirements and your task processing itself, or complete end-to-end latency as well. If you see here, the end-to-end latency is actually constantly going up and up. So this also tells you that there's a lot of buffering happening in your system. And this is not a very good thing to happen in a system as well. So these kind of reports will actually help you to make better decisions on selecting the right architectural components and also making the right architectural decisions as well. Okay, so this is what I actually wanted to explain in this particular tutorial, and I'm going to share a step-by-step guide to practice this particular tutorial as well. So if you come across any questions, please go ahead and ask your questions in the chat window. Otherwise, I will actually move over to the next tutorial. Okay, so in this tutorial, what I'm going to do is I'm going to go back to the slides here. So in this tutorial, what I'm going to do is I'm going to model a flow control logic here for X on X off and credit based. So I'm going to combine both X on X off and credit based flow control in a single model. I'll be starting off with a credit based flow control algorithm, and then I'll be incorporating X on X off flow control as well into the same system. Okay, so initially I'll be starting off with a simple single channel communication, and then I'm gonna insert more complexity into this model. Okay, so as before, you need to have a digital simulator, and you can use parameters to define the how long you want to run. I'm gonna define the sim time here. I'm gonna mention this is gonna run for about 10 milliseconds or 10 milliseconds, something like that. And then what I'm going to do is I'm going to define that value over here. So as I mentioned earlier, to define a flow control, you definitely need two resources here. So you need an ingress buffer and you need an egress buffer. So what I'm going to do at this point is I'm going to model the resources here. So this is going to be my ingress buffer. Okay, I'm going to name it as ingress buffer here. So as I'm using only one channel for this particular, or for the initial case, I'm going to keep it as it is. And I'm going to change this priority as well. I'm going to use priority in my scenario. So this defines my ingress buffer. And I'm going to need a egress buffer as well that defines my destination resource. For example, egress buffer could be your processor, availability of your processor. And ingress buffer could be your IO interface. Okay, I'm gonna change this to priority over here. And the time that egress buffer or your processing resource is, in this case, we're gonna just define some number over here. I'm gonna say this is gonna take about 10 microseconds to execute. So I'm gonna keep it as it is. To make it more complicated, you can add additional logic as well in between. I'm gonna add a simple delay block to represent some intermediate delays that could happen between your IO interface and the egress buffer. I'm going to call this as, or I'm going to provide this value as 1 epo minus 8. So this defines my ingress buffer as well as my egress buffer. So now what I need is I need the traffic, or I need the workload that generates traffic for my system. So what I'm going to do at this point is I'm going to instantiate a traffic block. So as I had before, I'm going to keep it as it is. I'm going to use the default data structure. And this traffic is going to come about for every 1 microseconds, for example. Set this to fixed value 1. And the definitions of that particular task is going to be what is going to be the priority. So I'm going to set this to some random number. It can be a static number, it could be anything. So in this case, I'm going to assign priorities for every transactions that is going through. So it is going to be integer random value between 1 to 10. And then in addition to that, what else I need over here is I need to know, one second. So actually at this point I can keep it as it is. I may not really need much details here. So let's keep it as simple as it is. So this is going to be having a priority, and that goes to the ingress buffer over here. And at the output, I'm going to compute the latency at what time I have received and what is my end-to-end latency here. T now minus input dot time. I'm going to set this to double. I'm going to connect a time data plotter. Okay, so now this completes my ingress buffer and egress buffer communication over here. So if I go ahead and run the model, in this case, if I select this to true, in this case, if you see here, I'm actually receiving only one transaction out of my communication channel. The main reason is that the ingress buffer over here can be controlled to send the transaction out. For example, if I double click on this, I can actually see here that initial queue state is set to first token flow through. So it'll actually keep on waiting for the triggers coming in from the pop input port. If you receive any transactions or if you receive any triggers uh, corresponding to a particular queue that is defined in this buffer, then the transactions will be pumped out. So to show you that, what I'm going to do is I'm going to connect a traffic block over here. I'm going to call this as pulse. I'm going to generate for every 2 milliseconds, or sorry, 2 microseconds, I'm going to generate a trigger for the ingress buffer. So if I go ahead and run the model, you can see here, now I can see a lot of transactions that are actually going out of the channel. But this doesn't really model any credit-based or anything like that. So we keep on sending the data out of the ingress buffer without knowing if the processor is ready or if the destination device is ready. So to know that if the destination device is ready or not, so we actually incorporate the flow control algorithms to make sure that you're not losing any data in the transmissions. So what I'm going to do is I'm going to define a very simple script over here using our script block over here. I'm going to define a very simple script. For example, I'm going to define a while loop that will be on for all the time, and then we are going to look at if we have any transactions arriving at the ingress buffer. To do that, we have a function called get block status, and then we need to define the name of that particular buffer, and we are looking at ingress buffer, and we're looking at length of the ingress buffer, and we have only one queue here or one channel here. So that's why we are using one over here. And if we have anything, so that means it is greater, length will be greater than 0. And then I'm going to look at if the egress buffer is actually length of the egress buffer is under the threshold, right? So I'm going to define it as egress buffer, and again length and 1, and if it is less than threshold. So threshold value can be anything that you want to have. You can either define it as a parameter at the top level, or you can directly provide the number over here. So in this case, I'm going to provide it as 4 over here. And if that is the case, then you will be triggering, or you will be sending the data structures out from the ingress buffer. So I'm going to send the value 1 out of the ingress buffer. Okay, so I can define an arbitration clock as well. For example, I can define an arbiter clock, and this can be a parameter at the top level as well, but in this case I'm going to define it as a block level variable, and I'm going to define this as 100 nanoseconds, and I'm going to end this. So this is a very simple script that I have actually written here to control the transactions going out of the ingress buffer. So it'll keep on waiting for, it'll keep on checking if the egress buffer length is under the threshold, which means if you have enough resources to process, then you can actually go ahead and send the transaction out. Otherwise, keep on waiting. So I'm going to commit the changes here. Okay, so I'm going to run the model. Oops. So the reason for that is this particular script block requires a trigger here. Otherwise, we need to enable this as a self-start mechanism. So if I set this self-start parameter to true, it will trigger on its own and it will send the transactions out. If you see here, we are sending the transactions at every 100 nanoseconds, which means the ingress buffer is receiving the request at 100 nanoseconds. So that's why we are seeing a lot of transactions that are going out. So the major reason for this latency at 1.1 e power minus 7 is because the ingress buffer initial queue state is set to first token flow through. So that's why for the very first one, we don't really look for any arbitration. We just simply send out. But if I set this to first token and queue, I'm going to still look for the arbitration, and if my resource is available, then I'll be sending it out. If I run the model, now you can see the difference in the latency graph as well here. Okay. So now what we can do is we can actually make it much more complicated. So what we can do is we can actually model multiple channels of transmissions. For example, I can have about 10 different channels defined using a single ingress buffer block. Okay, and I would need a field to select to which channel that you're going to send and things like that as well. So to do that, what I'm going to do is I'm going to insert a concept called dynamic instantiation at this point. So dynamic instantiation, what it does is it likes to help you to create multiple instances of the same traffic or the same item that can be replicated multiple times. So what I'm going to do is I'm going to copy or use this particular transaction generators inside the dynamic instantiation. I'm going to run this at 10. I'm going to copy this over. I'm going to connect to a port, and what else I need here is I'm going to define a field called channel to identify from which channel I'm actually receiving the transactions. So there is a parameter called instance that is actually corresponding to from which instance that you're actually sending. If you have 10 different instances, so that could be 10 different traffic sources that are sending the transactions out. Okay, I'm going to define one more field called channel name, and it could be channel and plus it could be instance, something like that. Okay, so I'm gonna commit as it is, and now we have a dynamic instantiation block that can send transaction out of this block, and I can have 10 different channels or the IO interfaces that are generating requests over here. So in this case, I can set this to 10. In order to understand from which channel that I'm actually getting, I can actually set this to field as channel because it is already field that I'm using, and then I need to modify my script a little to make sure that I'm actually going through all the script or all the logic that I had to. Okay, I'm gonna just quickly copy the content over so I know to save some time. So what I'm going to do is I'm gonna use this. So I have already defined my queue as maximum of queue as 10. It could be the top level parameter as well. So this actually helps me to send all the transactions out of the ingress buffer. For example, if we have, it'll keep on looking at all the buffer or all the channels that you have defined in the ingress buffer in a round robin fashion. So it'll immediately pop out the transaction from a particular channel. Okay, so I'm gonna commit apply here. So now what I'm going to do is I'm going to run the model, try to understand what is going to be. Oops. Need a field. Just forgot what's the name. The CH name that I need to send it out from the or to the right port. Okay, so here we have one more error. So the error message tells me that there is no field called egress threshold, so which must be defined as part of my parameter. For example, I can set a parameter at the top level and I can define it as egress threshold, and I can set this to value, whatever the value that I need to have. I set this to 4. I'm going to run the model, try to see what happens. So here you can see the latency differences now. So now we are actually not having only one channel that is being modeled here, but here we have multiple channels that are being actually modeled. Sorry, I need to have this set to 10 here. Run the model. So if you see here, now I actually have 10 different triggers or the transactions or IO interfaces modeled using a simple dynamic instantiation block. So if I set this or enable this, you can actually see that there are about 10 multiple instances of the same block is being generated. Okay. So this is how we can actually model a scenario. So in this case, what we have done here is we keep on looking at the availability of the egress buffer, and if the egress buffer is available, then ingress buffer will actually send the transaction out. So this is a kind of simple credit-based flow control mechanism. So now what we can do is we can actually incorporate a X on X off based flow control as well. For example, for that, what I need is I need additional queues. So I can name this as X on queue. X on queue. And here also you can have multiple channels, but for this, I'm going to stick with a single channel. I set this to priority. Again, I need one more block or the buffer that models the X of Q. I'm going to set this as it is again. So now these X on and X of Qs can be actually controlled by providing right values or trigger values to the pop input port of X on and X of buffers. So what I'm going to do at this point is I'm going to instantiate a traffic block again. I'm going to generate the data structure called pulse. So what I'm going to do at this point is I'm going to say for every 20 microseconds, or the first one will actually generate at 20 microseconds. After that, I'm going to generate at certain rate. For example, it could be every once microsecond, I'm going to generate the transaction out or the trigger out of this Exxon buffer. Okay, so but you can't really simply send out the transaction out of your Exxon buffer because you need to know the state of your XOF buffer. To do that, to identify if your XOF buffer is having sufficient space or processing resources, then you can actually send it out. So to do that, what I'm going to do at this point is I'm going to define a function called getBlockStatus, and if your XOF buffer length is less than, it could be the XOF threshold limit. So in this case, I'm going to set this to, for example, I'm going to set this to 2. I'm going to delete all these details here. Okay, so if I have, I'm going to change this to integer value. Okay, and now what I'm going to do is I'm going to pop out transaction out of the XOF buffer at a certain rate. So this can be actually controlled again. But in this case, what I'm going to do is I'm going to generate or send out at certain rate here. So I'm going to call this as 20 microseconds. And then you have your XOF rate. For example, it could be every 10 microseconds. And you're going to send it out. So now here, if you notice here, these Exxon and XOF buffers are actually controlling the transactions that are going out. If you're actually having sufficient space in your XOF buffer, then your Exxon buffer will actually send the transaction out. Otherwise, it will keep on waiting or it will be buffering in the Exxon buffer itself. Okay, so I'm going to run the model, try to understand how it looks. So if you see here now, the end-to-end latency is actually quite different. So earlier we actually had about 5 microseconds or something like that, but now the maximum latency is about 60 microseconds of latency here with a combination of multiple buffers and things like that. So this actually provides you information or details on how exactly you can create an arbitration algorithms or the kind of control algorithms, flow control algorithms with VisualSim and understand how exactly this is going to work with your real system scenarios itself. Okay, so one thing I missed out in this particular model is that ability to debug your system itself. For example, to debug, we actually provide multiple approaches. One thing is that you can debug or listen to a particular block and try to see what is really going on. For example, if I listen to this script block and if I run the model, I can actually see that what exactly is happening inside that particular script block, and I can easily debug what is really happening. Okay, so if I have multiple complex computations that are actually performing, or I might be waiting for another task to get completed or some other trigger from some other block, you can actually easily monitor in this particular way. And also you can look at if you're if you want to look at whether you're actually receiving the right values at any port. For example, you can right click on any port here and select listen to port and run the model, and you can see what exactly the value that is coming out of that particular port. It could be the complete data structure, or it could be any integer or double values as well. Okay, and also you can do additional things such as you can set a breakpoint and try to debug what is really happening. So for example, you want to understand before entering this particular block, you want to stop the simulation and try to see what is going to be the impact of that. Okay, so that is one thing. And in addition to that, what you can do is you can actually enable the animation as well. So this tells you how exactly the sequence of activities that are actually going across in the model. Okay, so one more important feature would be the ability to trace this complete simulation activity in the model and try to understand how many events that are generated and what is the performance of the model itself. So in order to do that, you can do a listen to simulator, and this provides you complete okay um, need to unselect this stop entry. I'm gonna open up this again. Okay, so this actually tells you that what is the sequence of activities that are happening in the model itself. Okay, so there's not much activity. Wonder why. Okay, so here it goes. So if you see here, this actually provides you a complete detailed information on at what timestamp you are actually running or you're triggering a particular block itself. Okay. Also at the end of the simulation time, it actually provides you information on what is the walk log time that you have taken versus the real time or things like that. And also it'll actually allow you to understand how many events that are being generated and the memory utilizations and things like that as well. Okay. So this completes today's training program. So I wanted to keep it very simple. So initially we looked at an embedded board design with multiple tasks and multiple dependencies that are available in the model. And also after that, we actually looked at a way to develop a flow control algorithm and trying to work with or trying to understand the kind of bottlenecks that you may come across and things like that. So this actually provides you information on how you can start off with a performance level modeling and what are the values that you can actually get out of these simulation models as early as possible in the design process. Even if you don't have much information about a particular piece of information, you can actually uh, keep that at a very high abstraction level and you can still go with the modeling of your complete system with whatever the available resources that you have with you. Okay, so this concludes this today's training program, and if you have any questions, please post in your questions in the chat window. I can actually answer those questions now.